right. Good afternoon. And those of you who do not know me, my name is Ali Kujuri. I'm one of the organizers of this lecture series. And then the two other main organizers are Mr. Sharam Mariwani and then also Ms. Kate Lab, who I'm really thankful for their support. Let me welcome you all, especially our guest speaker, to be attending this second lecture for this academic year. And in fact, it is the 137th lecture since the time we started in 2006, believe it or not. How about that? Yeah. Okay. Two short announcements before I introduce our guest speaker for today. And first, the pizza is going to come. I mean, it's a good one, right? At 5:30, right after the lecture. The next lecture will be on Thursday, October the 4th, titled Basic RF Measurements and Terminology by Mr. Weilin, Senior RF Hardware Design Engineer at National Instruments. Our guest speaker for today is Dr. Somayeh Sojoudi, and the title of her talk is Learning Large-Scale Sparse Graphical Models, Theory, Algorithm, and Applications. Dr. Somayeh Sojoudi is an assistant professor in the departments of Electrical Engineering and Computer Science and Mechanical Engineering at UC Berkeley. She is also the faculty of Tsinghua Berkeley Shenzhen Institute. She received her PhD degree in Control and Dynamical Systems from California Institute of Technology in 2013. She has worked on several interdisciplinary problems in optimization theory, control theory, machine learning, data analytics, and power systems. Dr. Sojoudi is an associate editor of the journals of IEEE Transactions on a Smart Grid, IEEE Access, and Systems and Control Letters. She is also a member of the conference editorial board of the IEEE Control Systems Society and a recipient of the 2015 Informs Optimization Society Prize for Young Researchers and a recipient of the 2016 Informs NRE Energy Best Publication Award. She was a finalist as advisor for the Best Student Paper Awards at the 2018 American Control Conference and a finalist as a co-author for the Best Student Paper Award at the 53rd IEEE Conference on Decision and Control 2014. So here she is.
Thank you so much, Dr. Kujuri, for the nice introduction. And hello, everyone. It's a great pleasure to be here today. So this talk is about learning large-scale sparse graphical models. Learning graphical models is actually a conic optimization problem. So before I talk about this, before I talk about how we can solve this problem, I'd like to briefly review conic optimization, talk about the applications of conic optimization in a lot of really exciting domains and areas. So optimization plays an important role in design, analysis, and modeling and operation of real-world systems. Once a real-world problem is formulated as an optimization problem, the main challenge is how to solve it efficiently. For example, if you want to solve a traffic control problem, the question is, can a traffic problem, control problem be solved in real time? So the complexity of solving this problem is related to the non-convexity of the problem. So it's related to the notion of convexity. So let me remind you what convex optimization is about. For example, for convex optimization, if you want to find a global minimum for a convex optimization problem, it's always easy using a descent direction, for example, no matter where. So this is an example of a convex optimization. No matter where you start from, using a descent direction, you can find a global minimum of this function. But finding a global minimum for a non-convex optimization problem is always challenging. challenging and it's hard. So for example, if you start from different points, you might end up at a local minimum, which could be far away from a global minimum of this function. So non-convex problems are difficult to solve to global optimality, both in theory and in practice. But what is interesting is that most real-world problems are non-convex. For example, in electricity networks, security constraint, optimal power flow, unit commitment, these are problems that are non-convex. In machine learning, deep learning, Bayesian inference, clustering, these are problems that are non-convex problems. In transportation, for example, traffic control problem is a non-convex problem. In control theory, problems such as robust control, optimal distributed control are examples of non-convex problems. But how do we solve these non-convex problems in practice? Well, practitioners commonly use local search heuristics for solving these problems. Conic optimization is a systematic approach for solving non-convex problems to global optimality. So conic optimization is minimization of a convex objective function or function subject to a set of conic constraints. And several classes of convex optimization are special cases of conic optimization. For example, linear program, quadratic programming, semi-definite programming, or SDP. These are special cases of conic optimization. So conic optimization can solve non-convex problems through reformulations and relaxations. To talk about the convexification or relaxation, consider, for example, a feasible set of an optimization problem which is composed of these disconnected components. So what the convexification technique does is just make this set bigger and makes it convex. And so this idea is done through the idea of lifting, which is done by adding more variables and constraints to the optimization problem. In 1980s and early 1980s, it's been shown that we can make a strong theoretical guarantees on the tightness of convexification when the problem is posed as a conic optimization problem. So that shows the power of conic optimization. So starting from early 90s to around mid-2000, conic optimization was applied to really broad sets of non-convex problems. For example, nonlinear stability analysis and optimal control in control theory, inference in statistics, and integer and mixed integer programming in operations research. So conic optimization has also been applied to very important classes of problems, for example, max cut in graph theory, or compressed sensing and matrix completion in signal processing. So conic optimization comes up with some approximate solutions whose complexity is very close to the best that we can do, and that's the information theoretic complexity of the problem. In early 2000s, Jean Lasserre and Pablo Perillo used conic optimization for more general classes of problems, and that's polynomial optimization, where we minimize a polynomial objective subject to a set of polynomial constraints. This made convexification technique applicable to a wide range of problems. So this conic relaxations has a lot of applications, and one very exciting application of these convexification techniques is for power systems operation. So in power systems, optimal power flow problem is a fundamental optimization that should be solved annually for system planning, daily for day-ahead commitment, and every 5 to 15 minutes for real-time market balancing. So this is a very fundamental optimization problem in power system, which is non-convex. So the current practice for solving this optimization problem relies heavily on local search heuristics, but a study which has been done by Federal Energy Regulatory Commission, or FERC, has shown that the inability to find a global optimal solution for this power optimization problem costs the electricity market tens of billions of dollars every year. So you can see that this is quite expensive for power systems. Now, so just to briefly review the SDP relaxation or semi-definite programming relaxation for polynomial optimization, if we have a polynomial optimization, we can reformulate it as a quadratic optimization by introducing new variables. For example, this is a quadratic canonical form of a general polynomial optimization problem. We have a quadratic objective. So the trick here is to reformulate the objective as, so we have x transpose m0x that we want to optimize. We can reformulate it as the trace of m0xx transpose. And And then we can replace the XX transpose with a matrix W. Now W is a product of two vectors. So that's a positive semi-definite matrix, and it's rank 1. So the rank 1 constraint here makes the SDP, this optimization problem, in fact, non-convex. So the way that we can get rid of that, or make the problem convex, is to get rid of the rank 1 constraint. And this is known as semi-definite programming, or SDP relaxation. So in this formulation, we can see everything is linear in matrix W. It's a convex problem. We can solve this easily. Now, if we solve the SDP relaxation and we are able to find a solution that is rank 1, we can map it back to a global solution to the original problem. Right? So we can recover a global solution if the SDP relaxation has a rank 1 solution. And in that case, we say that the SDP relaxation is exact. But SDP relaxation is not exact in general. And but what was very interesting was that in 2010, Lavai and Lowe observed that the SDP relaxation is exact for IEEE benchmark examples and several real data sets. And later, we proved that for power distribution network, which is an acyclic graph, we can guarantee the exactness of SDP relaxation under the assumption that the price of electricity is positive. And for the transmission network, we also have cycles in the network, so the network is basically cyclic. We need some extra assumption that implies we need to have more transformers in the power system so we can make the SDP relaxation exact. And then later on, we deployed physics of power networks, and we observed that that reduces the computational complexity for power optimization problems in general. But SDP, yes.
Can you please tell us about what is it that you want to optimize now in the power system in the previous graph? Yeah, what is it that you want to optimize now here?
So for power system, for example, what we want to optimize is the cost of electricity, because we have demand and we have supply.
Right.
So we want to optimize the amount of power that needs to be generated, and also we want to minimize, for example, the cost of electricity in some way.
Right.
So that's what we want to optimize in the power system. But we also have a lot of constraints in terms of, for example, the capacity of the power lines is limited. We cannot send too much electricity over the power lines. And so that adds extra nonlinear assumptions to the optimization problem. And that's what makes the optimal power flow problem a non-convex problem, and then we want to solve it through SDP relaxation by linearizing the problem.
Right. But when you want to optimize power, this means that you want to reduce the inductive, it is a song, but then somehow, make it like a resistive type of thing. So is it the idea? You can also do that, or it doesn't care?
So basically, we have a lot of because we have like a power network, right? A power network, and on one edge we have the power generators,
right.
And then on the other edge we have the consumers that want to. So the behavior of consumers changes, and also the electricity network has a lot of, let's say, uncertainties, right. and the dynamic changes and so on. So that's something. So we want to make sure that the amount of power that needs to be generated by the generators is optimized in some way.
Okay.
Yeah. Okay. So that's the goal.
Thank you.
Yeah, because or in other words, if you, for example, generate extra power, then some of this has to be like for example, sort of stored. So, and then the price of storage and all these things would come into play. So that's why there's that adds a lot of extra assumptions to the problem. Yes.
So if I understand you correctly, your problem that you're really working on has multiple generators, multiple transmission
Exactly.
lines and switches, and you're looking for what's the best way to optimize it in terms of the combination of all these operating under the conditions that are required at that moment.
That's true, that's true.
Yeah.
That's a very nice explanation, that's true, yes. And now with having a smart grid, for example, moving towards a smart grid, we are adding more uncertainty. We are adding new type of generators actually that depend on solar and wind and so on. That makes the problem much more interesting and complicated in some way. Yeah. So But the observation that we can make here is that the SDP relaxation may not be exact for larger scale systems. For example, the price of electricity might not be always positive. And so in that case, we need to come up with a trade-off, to come up with a simpler algorithm, but lose some optimality. So the way we tried to tackle the problem was to come up with some sort of penalized SDP to find a near global solution to the original power optimization problem. We applied the algorithm to a polished grid for different network structure or configurations on different days, and we were able to guarantee the optimality of the solution by at least 99%. So SDP looks very promising for energy applications. And SDP revitalized the area. There have been several follow-up work in academia on this line of research, and also this work has received a lot of interest from industry. So another perhaps more recent work that my group has been working on is on studying the performance guarantees for local search algorithms without convexifications. What if we don't want to convexify and that we want to use a local search heuristic or algorithms for solving non-convex problems? So we, in two of our recent work that has been accepted and is going to be presented at NIPS conference, we have studied some classes of problems for which, when the conic optimization works, we can also use local search algorithms, which is faster, and we can solve the problem efficiently. So conic optimization has a lot of applications. I just mentioned one in power systems, but it has been used for a wide variety of applications. Transportation is one such application. But it also has a lot of applications in machine learning. For example, kernel-based support vector machine is a popular classifier, perhaps one of the most popular classifiers in machine learning. This is an SDP. The other problem in machine learning is graphical models. Learning graphical models leads to a conic optimization problem, and that's the focus of the rest of this talk. So graphical models have a lot of applications. For example, they've been widely used in social networks for modeling the social network and connectivity. It has been used in neuroscience for modeling the human brain, how different parts of the brain interact with one another, financial markets, in medical diagnosis. So in all these applications, we are dealing with massive amounts of multivariate data, and often we have billions of variables, and in most of these cases, we have limited number of samples, and we have no direct access to the structure. So the goal of graphical models is to understand the underlying structure of the data that we are dealing with. So the problem has been studied to different, or can be studied into different contexts. For example, in the context of control theory, this can be studied as in the form of system or topology identification. In machine learning, the problem can be studied in the context of network inference. So in network inference, we want to find the graphical models that shows the statistical interactions between systems components. In a graphical model, every node represents a random variable, and an edge represents the statistical relationships or connections between the two random variables. The literature on graphical models is very rich, and it goes back to more than two decades ago. And there's different applications of graphical models that we've been studying. One is in transportation. For example, in this context, we want to see, using graphical models, how traffic in one street statistically affects traffic in other streets. And this information in particular is useful for real-time congestion control and also for traffic forecasting. Another application of graphical models is in neuroscience. Since there is no first principle to model the human brain, graphical models allow us to model the brain using a data-driven approach, which is based on learning graphical models. So, so this is basically useful for understanding how the human brain works, and we can also use this information to study, or this modeling to study different neurological disorders such as epilepsy. Now, learning graphical models is a conic optimization. For example, if you want to learn a model with 1,000 parameters, that would lead to an optimization problem with 1 million parameters. So, as you can see, this idea is not scalable for larger scale systems. The problem has been studied extensively from both, actually in the statistics, from the statistical properties of graphical models has been studied very extensively. There are some work on the optimization aspects of graphical models as well, but optimization rather has been studied less compared to statistics, and that's the focus, and optimization basically is the focus of the rest of this talk. So this is the outline of the rest of the talk. I'd like to briefly introduce graphical lasso, which is a popular algorithm in machine learning for learning Gaussian graphical models, especially in the regime where we don't have a lot of data. So I'm going to show you that graphical lasso is actually a conic optimization problem. And then I'm going to show you the equivalence of this conic optimization with another operator, which is a simple operator called self-thresholding or thresholding technique. And then I'm going to use this equivalence between the two techniques to find a closed form solution for this optimization problem without solving the optimization directly. And that's an exact solution when the graph we are looking for is acyclic. And then that solution would serve as an approximate solution for general sparse graphs, especially when we have cycles in the graph. And then I'm going to extend our results to chordal structures, and I'm going to introduce what chordal structure means and what kind of graphs are called chordal. And finally, I'm going to extend the results or design numerical algorithms for arbitrary graph structures. So let me start by briefly reviewing graphical lasso. So consider a multivariate Gaussian random vector X with zero mean and covariance matrix sigma. The inverse covariance matrix, or sigma inverse, is also known as precision matrix. In an undirected graphical model, every node represents a random variable, and an absence of an edge means that the corresponding random variables are conditionally independent. Okay? So for a Gaussian random vector, every two random variables are conditionally independent if and only if their corresponding entry in the inverse covariance matrix is zero. Okay? So conditional independence between two random variables implies a sparsity in the precision matrix. So as we have more conditionally independent random variables, we expect to have sparser inverse precision matrix, right? And when I talk about sparsity, I mean we have a lot of zeros in the matrix. So in practice, we don't have the true covariance matrix. What we have is limited number of samples from which we can form a sample covariance matrix. So how can we estimate the precision matrix? Based on maximum likelihood estimation, we can form the problem as a maximization or an optimization problem, which is maximizing the log determinant of S minus the inner product of sigma and S. Yes.
Is the precision matrix the inverse covariance?
Yes, that's correct.
Oh.
Yeah. So the maximization of log determinant of S minus the inner product of sigma and S, subject to one constraint, which is S has to be non-negative. So here, sigma is the sample covariance matrix formed based on the data that we have, based on the measurement, and S is the matrix that is supposed to estimate the inverse covariance matrix or the precision matrix. So in classical theory, the maximum likelihood estimation converges to truth as the number of samples goes to infinity. But in practice, we are often in the regime where the number of samples is very limited and is very, very small. And in that regime, the sample covariance matrix is rank deficient. And in other words, it's ill-conditioned. So the maximum likelihood estimation doesn't even exist in that scenario. But how can we resolve the issue for such cases? So going back to the fact that we know conditional independence implies a sparsity in the precision matrix, we can impose an L1 penalty to the objective of the optimization, so the lasso, which is known as lasso penalty. This makes the solution sparse in some way. So lambda is the regularization parameter. By increasing lambda, you increase the level of sparsity of the solution S, and that also makes the problem well defined. So this optimization problem is known as graphical lasso, and this is a conic optimization problem. So now that we formed this conic optimization problem, the next question is how graphical lasso can be solved in practice. So in 2007, there were papers that used interior point methods and block coordinate descent to solve graphical lasso. So these are some techniques that people use for solving optimization problems. But the complexity of these two methods is of order of n to the 6 and n to the 4 respectively, right? And but the G-lasso and Quick are the most commonly used and fastest known algorithms for solving graphical lasso, and then they also have complexity of order of n to the 4, and epsilon here is just the accuracy of the solution. Okay, so in machine learning and data analytics, problems that we are dealing with are often very, very large or extremely large. So n to the 4, you can see that it's going to be an enormous number, right? So this is basically is not possible using this method to solve graphical lasso for large scale problems. But the question is, what's the true complexity of the problem? Well, the complexity cannot be lower than n squared, because even reading an n by n matrix has this much complexity, has n squared complexity. So what I'm going to show you in this talk is that under mild assumptions, the problem can be solved very efficiently. So the first results that I would like to show you is about equivalence of this conic optimization technique with another operator, which is a simple operator known as thresholding. But before that, I'd like to define a bunch of notions. So we had to come up with some definitions in order to come up with results that talks about the equivalence of the two techniques. The first definition is what we call inverse consistent matrices. We call a matrix M inverse consistent if you map it to a graph. For example, the graph representation of the matrix looks like this, right? So for any non-zero, so the number of nodes in the system shows the dimension of the matrix, and an edge between two nodes means that their corresponding entry is non-zero in the matrix. So the matrix M is called inverse consistent if there is another matrix N that if you map it to a graph, the union of the two graphs would be fully connected. In other words, the two graphs complement one another. And if you look at the intersection of the two graphs is an empty set, right? There's no, so the intersection of these two graphs, they don't have any edges in common. The third condition is that if you add the two matrices, that would result into a positive semi-definite matrix. And the last condition is that the support graph of M plus N inverse should be equal to the support graph of matrix M. And by support graph, I just mean the graph that is shown here. Now, the second definition, so if all those conditions are satisfied, we call our matrix inverse consistent. The second definition is what we call sign consistent matrices, and for that there is some sign conditions that also need to be satisfied in addition to the other four conditions that I provided in the previous slide. So another definition is about a function beta. So beta is a function that has two arguments, g and alpha, and g here is a graph, alpha is a scalar. So consider the set of all inverse consistent positive semi-definite matrices M that we defined in the previous slides, such that the support graph of matrix M is equals to G, and the maximum entry or maximum of this matrix M is upper bounded by alpha. Then the beta of G and alpha is the maximum of the N matrix that we introduced in the previous slide. So there's an operation which we call soft thresholding, and then I'm going to discuss the performance of graphical lasso or compare it with this technique. So in soft thresholding, again, consider the graphical lasso, this optimization problem. So if you have a sample covariance matrix like this, you can map it to a graph. So in this case, this is a very dense matrix, and its corresponding graph is just a fully connected graph. So with soft thresholding, what we do is that we look at the entries or the magnitudes of entries of this matrix, and if those are greater, some entries are greater than, or if the entries of this matrix are greater than the lambda, which is the regularization parameter in the optimization, we're going to keep those entries, and then we're going to threshold out the rest of the entries. That means that we replace them with 0. Okay, and then we're going to adjust the values of the matrix just by the sign of the corresponding entry. So we call this matrix the soft thresholded sample covariance matrix. All right, so now what we can show here is that given k is the number of edges in the graph that we are looking for. Given k, graphical lasso and the thresholding, the soft thresholding technique are equivalent, meaning that if you solve graphical lasso, you will get a solution. If you just simply solve threshold, the sample covariance matrix, you would get another solution. If you compare the two graphs, they have the same structure. Okay, they have the same support graph. If there exists a regularization parameter within this interval, which is defined by the k and k plus 1 largest magnitude of sample covariance, for which some conditions are satisfied. The first condition says that if you add the soft thresholded matrix with, to an identity matrix, the resulting matrix should be positive, semi-definite, and meaning that it has, so just to define positive definite matrices, that means that has to have positive eigenvalues, and also it's sign consistent. And also in addition to that, the following condition should hold. That means that if G is the support graph of the thresholded matrix, and alpha is defined this way, then the beta function that we defined before should be upper bounded by the regularization parameter and k plus 1 largest magnitude of the sample covariance matrix. Now we can show that for a graph, for every acyclic graph, this inequality turns out to be this equality. So in other words, beta is going to be this quadratic function, right? So sigma 1 is the largest magnitude of sample covariance, lambda is the regularization parameter. So another question is how conservative these conditions are. We can show that a large class of residue matrices, or the matrices that are formed in this way, are positive semi-definite. And we can show that positive semi-definite matrices are sign consistent. So we can see that the first condition is likely to be satisfied for a large class of matrices. And then the complexity is mostly about checking whether or not this inequality holds. And if it holds, then graphical last on thresholding are equivalent. All right, so the next result I'd like to show you is about a closed form formula for graphs that are acyclic and have no cycles. Now, similar to the conditions that we are given in the previous theorem, with the exception that we are assuming that support graph of the thresholded matrix is acyclic, we can solve the graphical lasso. In fact, we can just find a closed form solution to the graphical lasso without solving the optimization problem, and that's equal to this function given here. So the optimal solution of graphical lasso under these conditions is equal to this. So here we were able to find a closed form formula for a conic optimization problem without solving the problem itself. Now we can also show that, so now I'm just going to move on to the cases where we also have cycles in the network. So if it's acyclic, we know that we already had a closed form solution under very mild assumptions. Now, how about the cases where we have cycles in the network? Now, suppose, for example, again, similar conditions as we've seen before. We assume the regularization parameter is defined between some intervals, and these conditions that we've seen before is satisfied. Now, we can see that the closed form formula that we found for acyclic graphs serves as an epsilon approximation for the optimal solution of graphical lasso, right? So, so what is this? So what is epsilon? Basically, epsilon is the error, which is very small for sparse graphs and graphs that are very close to be acyclic. So here we were able to find a closed form formula as an approximate solution for a conic optimization problem, which is a very important optimization problem in machine learning. So I'd like to show you some simulations in some real data sets that we tested. So the first data set is about functional MRI data that basically shows brain activities of human brain, actually. So here, what we did was, so the goal here is, so we have 140 different disjoint brain regions, and we want to find the connection or the network that shows how different parts of the brain interact with one another. So this is from the resting state functional MRI data. So in order to find this connectivity in the context of graphical models, what we're going to do is to once solve graphical lasso, right? And another time, we're going to just use the closed form formula that we proposed and to see and compare the results that we're going to get out of these two techniques. So this graph here shows the approximation error. That means that as you increase, so this is lambda. Lambda is the regularization parameter. As you increase lambda in graphical lasso, you are increasing the sparsity of the solution, right? So you're getting sparser graphs. But as we can see, the approximation error, meaning that the solution that you get by solving graphical lasso and the closed form formula, the error between these two would go to 0, right? And that shows the similarity degree between the two graphs. So now we can see, so this is just highlighting the sparse regions where lambda or regularization parameter is relatively large. And in this case is more than half, you would get a very small approximation error. The second example that I'd like to show you is from California Transportation Network. Here we have a network with about 1,000 nodes, and we want to find a correlation between traffic at different parts of the freeway, right, using graphical models. And once we solve this using graphical lasso, another time use our approximate solution. And as you can see here, for large lambda, the number of edges in the graphs was was about like 7 times higher than the number of edges in the network. So we had a network of 1,000 nodes, about 7,000 edges. The error that we got by from solving graphical lasso and also using closed form solution is less than 1% in this scenario. And also, as you can see, by increasing lambda, the similarity degree between the two techniques increases. Now, we also extended our results to chordal structures. But just to briefly remind you about the chordal graphs. So chordal graphs is basically, so what I want to say before that is acyclic graphs are special cases of chordal structures. And it turns out that there's also a closed form formula for chordal graphs under certain conditions that are very similar to the ones that we found for acyclic cases. So this is an example of a chordal graph, but just to formally define what chordal graph means. So a graph with a chord for all cycles of 4 or more vertices is called a chordal graph. So what is a chord? A chord is an edge that is not a part of the cycle, but connects the two nodes in the cycle. For example, this is an example of a chordal graph. This is a graph that is not chordal because here we have a cycle of size 4, but these two nodes are not connected, right? So this is not chordal. But if you have a graph that is not chordal, how you can make it chordal? Through the idea of chordal completion. And the chordal completion says just add edges to non-chordal graphs and make them chordal, and that's called chordal completion. There's another notion that is important for developing the results of our work, and that's in graph theory known as tree widths. So tree widths, by definition, is one less than the minimum size of the largest click among all possible chordal completions of a graph. So this is one definition of tree widths. There are different versions. This is one version of the definition of tree widths. So, but what is a click? So we said that's the largest click. And a click is a complete subgraph of a graph. So for example, in this scenario, we have multiple clicks. For example, we have 23 one-vertex clicks, which are the vertices of the graph, and so on and so forth. We have 42 two-vertex clicks, which are the edges of the graph, and they just can continue this story. So that's the definition of click. So what we've shown here is that if, for example, the tree width of the graph is upper bounded by some functions, and also alpha, the scalar that we proposed or introduced before, is also upper bounded by a function of the tree width of the graph, then the beta function, if you remember, so beta was a function with two arguments, g and alpha, is upper bounded by a function of alpha and the tree width of the graph. So we found a formula for, or an upper bound for this beta function. And these conditions basically are likely to be satisfied for sparse large sample covariance matrices. Now with that, again, similar conditions as what we saw before, we can see that if the graph that we are looking for in this scenario is chordal, then under similar assumptions or conditions, we can say that graphical lasso and thresholding are equivalent. Okay, so if you saw graphical lasso and you also use thresholding technique, they would result in graphs that have similar or identical support structures. Now, if all these conditions are satisfied, the graphical lasso can be reduced to a maximum determinant matrix completion problem. And it's known that for chordal structures, the maximum determinant matrix completion problem has a closed form formula. Now, we applied this technique to several large-scale data sets, and we were able to solve chordal instances with as large as 3,000 nodes in less than 2 minutes. And then for the same data sets, we applied Quick and GLasso as I mentioned, these are the fastest known algorithms for solving graphical lasso. And we observed that the algorithms don't even converge in a 2-hour limit. Right? So we can solve the problem in 2 minutes. Those techniques cannot, those algorithms cannot even converge in 2 hours. Yes?
What machine was used to?
So it was just actually performed on a simple laptop.
Oh,
Yeah.
okay.
And actually, sort of the bottleneck is sort of the memory and so on. Yeah, that's a good question. So, so that's basically something that we were able to do with using the technique that we just proposed. Now, we would like to extend the results to arbitrary graph structures. So far, we talked about chordal structures. So in the case where the solution is not chordal, in our paper which was presented at ICML, we used a modest thresholding to get a supergraph and then embed that graph into a chordal graph and then propose a low complexity algorithm to find the right subgraph of the chordal graph. So using this technique, we were able to solve instances with as large as 200K by 200K in less than 2 hours on a simple laptop. So just to give you briefly an idea about the algorithm that we performed or we designed. So in the first step, we sort of compute a chordal embedding of the graph and then use that embedding to reformulate the maximum determinant matrix completion problem into a sparse chordal matrix program. And then we use a dual function and reformulate it as an unconstrained optimization problem, and then use Newton's method. And each Newton step, we compute the Newton's search direction using conjugate gradients. And this is basically just a summary of the algorithm and the way we solve the problem. So this shows basically the comparison of these algorithms and how fast you can solve the problem for large scale problems compared to the state-of-the-art algorithms, which is basically here we use Quick. And as you can see, so this curve here shows the performance of our algorithm, and this curve here shows the performance of the Quick algorithm. As you can see, our algorithm is almost linear time, so both pictures actually shows compares our technique with the Quick algorithm. As you can see, we can solve the problem in almost linear time, but the Quick algorithm quickly saturates, and you can see that it cannot handle the problem when it gets when it passes some certain limits in terms of the size. Just to summarize, optimization, as I said before, optimization is very important for the analysis, design, and operation of many real-world problems or systems. And so one main challenge in a lot of applications is that you're dealing with non-convex problems. I briefly talked about conic optimization, and conic optimization can solve non-convex problems to global optimality through techniques known as reformulations, relaxations, which is known as convexification technique. I briefly talked about the application of conic optimization and relaxation for power systems. Transportation is another important application that has significantly benefited from this technique. And also, I talked about the application of the conic optimization in machine learning, and in particular, I talked about graphical models. And as I said, graphical lasso is a popular method in machine learning for learning Gaussian graphical models. This is a conic optimization problem. We developed new notions of sign and inverse consistent matrices to find key properties of solution of graphical lasso. And we were able to find a closed form formula for this conic optimization problem, which is exact for chordal structures, and serves an approximate solution for arbitrary non-chordal structure or sparse graphs. And And then we also designed an algorithms which can be used for arbitrary graph structures and has a complexity of order of n squared, which is much less than the state-of-the-art algorithms that exist for solving graphical lasso. And we were able to solve instances of size 200K by 200K in less than 2 hours on simple lab tests. So before I start, I'd like to acknowledge my team, my students and postdocs, Salah, Richard, and Cedric, and my colleague at UC Berkeley, Professor Lavalle from IUR department at UC Berkeley, and also I'd like to acknowledge the funding agencies that have supported our research in the past. Thank you so much for your attention. I'm happy to take questions. Yes.
Now, in the example of the MRI that you showed, can you please tell us about what is it that you are looking for, what's it that you can optimize and so on, and what's the algorithm that you use? And by the way, I was astonished to see how many theorems you have defined. Really. Did you see
It's a theoretical research.
Yeah. Amazing. Yeah. Okay.
So that's a very good question. So basically the way it works for the functional MRI data is that basically we are working on resting state functional MRI, and the subjects are just lying in their scanner and without any activities. So the whole purpose is just to measure the brain signals and then see what's the correlation between activities at different parts of the brain. So the way that it's done usually is that for like every fMRI image has some sort of voxels. There are some sort of techniques, like for example, the averaging that is being done to come up with some, to identify or segment the brain regions. So once we identify different brain regions functionally, we want to see what's the sort of the statistical relationship between, or the correlations between the activities at different parts of the brain. Like for example, we want to see whether the auditory cortex communicates with visual cortex or other parts of the brain, and how does it work. So now the whole idea here is to use or model the brain using graphical model, because there is no first principles for the model, for the brain to model the human brain. We are relying on the data-driven approach. So based on the data that we are collecting, we want to identify how different parts of the brain basically interact with one another. And graphical lasso here was used to sort of give us that graph structure that would tell us what parts of the brain are interacting with one another.
Is there any way that you can go and then find where the nodes are, define where the nodes are, and how many are, and how far they are from each other, and so on?
Exactly, yeah. So these are all the techniques that have been really well studied and developed in neuroscience community, and people often do it for studying the brain, yes.
Yeah. And then for the algorithm, I bet you have written a number of algorithms and so on for different applications. Now, are you using some algorithms, some other programs to bring together? Because I bet defining the lines of codes here now is going to be huge. And then I don't know how many lines of code you're going to, you need to write to do something like this.
Yeah, so basically for all these algorithms that we design, we also write codes and test them on different data sets to see how they work, and also compare it with other techniques that exist to make the comparison. So that's exactly what we did here too.
Right.
Yeah.
Okay, good. Yeah, our students have not taken any graph theory course, and then I bet it's going to be tough for all of us, but that is what it is, and then that's what they can do all sorts of studies, as you mentioned, in traffic analysis in the brain, probably cancers, cancers in brain and whatever.
Tons of applications, that's true. Yeah. Yes.
Yeah, of all the application areas that you mentioned, what have you focused the most on?
So basically, because the algorithms that we design are really broad and can be applied to different applications, but the data sets that we just tested and the ideas were on fMRI and also the transportation that I've shown here. Yeah, but then the goal is to sort of work on other important, interesting applications like biological networks, for example, to see how we can model those.
Sure.
Yeah.
Okay. I'm particularly interested in financial models. What work has been done there?
Well, actually, there's tons of things that have been done in the financial markets, and graphical models have been extensively used in that area. But I haven't tested our algorithms on those data sets, but maybe in the future, yeah.
Now, have the power utilities actually expressed strong interest in this, or?
So for power systems, you mean?
Yeah.
So power systems would be also another very interesting application, the case where the data you collect from nodes of the network in some way, once, for example, let's say there's a power line out because of a fault in the network, then the network topology identification would be definitely something very interesting in this context.
I would think this could be very useful, and then
That's
they should
true.
be funding some of it.
That's true. Yes.
Does when you do the chordal completion, does that not introduce like a significant amount of error, or how is that handled?
So basically, once we do it, of course, you would get some sort of approximation in some way. That would maybe, result in some sort of, but then usually, so what kind of errors are you talking about?
Well, I'm not quite sure, like basically what's the side effects of doing the chordal completion, because you have like your set, and then basically you're adding other connections, right?
Yeah, but if you're very close to being chordal, and there are a lot of examples that exist that are very close to being chordal, so the error is very small. Yeah.
No, and then there was a slide that you had about the application. Could you please go to that, and then maybe we can have some questions there. Because I mean up front, I suppose. It's good at least to see the applications that we had.
Oh, so the applications that we tested are.
Yeah, I mean at the very beginning you were talking about
Okay. Let's see. Are you talking about the applications in social networks?
For example, let's just talk about that. The neuroscience.
Yes.
It's basically is it that let's say the memory and aging center. I mean, in UCSF,
Yeah.
there is a memory and aging center, right?
Right.
And then they do all sorts of things and so on to see the progress of Alzheimer's.
That's right.
All right. So in that application, I mean, can you tell us, I mean, how this thing can be used so that to see how basically the brain cells and so on, the neurons are damaged and so forth, and then this Alzheimer's goes further?
Yeah, that's actually a very interesting, very nice question, and that brings me back to the memories that I actually.
Because I need it. I need it for my brain.
Yeah, so I actually spent some time at NYU Medical School, so I was actually working with neurologists who were interested in learning more about epilepsy in particular, because I was a part of Epilepsy Center. And the idea there was that they wanted to understand or sort of use these graphical models to better understand, the problems underlying, this kind of diseases. Like epilepsy was one example, and aging and Alzheimer's disease, certainly other very interesting applications. And there's actually, there's a lot of work done in neuroscience, people using graphical models to better understand these kind of diseases. And that helps basically the neurologists and neurosurgeons to better identify the parts of the brain that are problematic, and try to come up with ways to sort of treat these patients.
Right.
So yeah, there's been a lot of work done in that direction, absolutely. And like in the context of epilepsy, I mean, I would be happy to explain it a little bit more details, maybe technical details.
A few moments, why not? Go ahead.
So basically, the way it works is, for example, in epilepsy, the goal is to understand what part of the brain is basically creating the seizure, right? So what part is in the brain is causing the problem. And based on graphical models, you would expect that by looking at the graph and also studying the properties of the graph, like for example, the nodes that have the highest sort of concentration in terms of connectivity to different nodes, those could be potentially those that could create the issue. And so through these sort of studies, people try to identify the parts of the brain that don't work well and try to sort of come up with ways to treat it.
Right, good. And then in the social networks, what's it that you are looking for?
So in social networks, so graphical models have been, so there are all sorts of forms of graphical models. You're just focusing on one Gaussian graphical models and so on. So graphical models in general has been studied in different contexts, like social networks, another way of identifying the connectivity between different individuals or entities and so on. So that's just sort of one application. There's a lot of work done in that direction as well. Yeah, but once we talk about graphical models also, it's a very general notion. It comes with a lot of different statistical properties and forms and shapes. And we have directed and undirected graphical models and so on. And a lot of assumptions on the type of measurements that we have.
I bet the Russians have used a lot of your theorems in this concept for the previous election. No, really, I mean.
So if you're using a conic optimization for your algorithm, how do you weed out things like bad local minimums or saddle points in your data?
So in the form that we are talking about, like for example, that's actually a good question for conic optimization. So we are talking about two different sets of problems. Once you can use conic optimization as a relaxation technique for non-convex problems, once the problem already is a conic optimization, which is convex and everything is fine, right? So in the context of graphical model that I presented, everything is convex and nice. So there's no approximation in there.
But
So that's the two things that you need to distinguish, sort of.
Sparse modeling, it becomes non-convex.
So in the first part of the talk, when I talked about power systems, for example, we are dealing with a nonlinear, non-convex problem, and then you have to come up with some sort of relaxations to come up with algorithms that you can sort of solve. And then there will be some notions about sort of duality gap, which means how far the solution you get out of relaxation is from the solution that you would expect to get from the original problem, right? So that's a different context. So once there is a problem that is not convex, you would use convexification techniques to make it convex. And there's another problem that's already convex, and you can solve the problem. Yeah, but then the contribution, especially on the second part here, is that you have a conic optimization problem, but you don't want to solve the problem. If you have a closed form formula, there is no need to solve the problem, right? So using a sort of a closed form, this rarely happens in optimization that we have closed form solutions. We do have closed form solution for optimization, but not in general. Once you look at the general class of conic optimization, there is no closed form solution for that. And here we were able to find a closed form formula for conic optimization, and that's something that makes it really exciting.
Okay, it's now 5:30, and I would like to thank Dr. Sojoudi for such an interesting thing. It's really, a complex thing. Really. Just thinking in it, makes us crazy. So thank you very much.
Thank you so much for having me.
Yeah,
Thank
well,
you.
okay.
Thank you so much.
Yeah,
Yes.
and then now we have the pizza, and we can now have